streaming right now. So at this point, what you see on the projector, as well as my voice, is going to be streamed to YouTube. So it will be stored on YouTube as well. Closed captioning is going to be automatically done after, I don't know, maybe an hour or two. I have no idea how long it takes for YouTube to update the closed captioning, but it will be closed captioned. All right, cool. All right, so first thing is to show you guys, how to get to the video. So you just go to youtube.com/someprofs, and that's my channel. I share this with some other professors, but I think I'm the only one left actually recording new content. So if you click on videos, it will show you the video content that I have recorded. There are more than 2,000. You're more than welcome to watch anything here. But you can see this one is live. If you click on it, it will actually show what I just talked about or what the screen has about 20 seconds ago. It's kind of cool. And this is from the morning class. This is from my morning assembly language programming class. So this is how you can review things that I talk about in class, which doesn't replace taking notes in class. So you still want to bring your notebook, writing instruments and stuff like that, except things that are long, complicated, you don't need to waste your time to write that. Okay? What you need to write down are things that is happening in your head, because whatever I say is recorded. Whatever I do on the computer is recorded. Okay? But your understanding, the whole process inside your head, to understand the concept, that you have to write down. Okay? Because if you don't write that down, you might forget, okay, your own understanding of the material. The other thing that is helpful to write down is basically just a timestamp. In other words, if I start talking about, let's say, bijective functions, okay, which is a topic that we will talk about in a few weeks, just kind of jot down the time, okay? 4:45, text starts to talk about that concept. Why do you think that might be helpful? So you don't have to watch the whole video again just to find out where the starting point is. So you just fast forward the video to about 45 minutes past the beginning, and bam, you have it. Does that make sense? Okay, cool. All right, so now that you know where to find class recording, and we are recording at this point, I'm just going to go through some of the syllabus material, but I will rely on you guys to watch and read some of the other material. So this way I don't use all the time in class to talk about this. This is all on Canvas, so I think it is already published, the Canvas website. So you just have to sign in. If you're on wait list or waiting to get into the class, I will send you a permission number. As long as the classroom fits, I can add everybody to the class. Is that okay? Okay, so this is section dependent information, which depends on which class I'm talking about. So this is cisp440, discrete structure for computer science. So this is all stuff that is only relevant to this class, including the time, date, when we meet in this classroom, and so on. This part here is what we call the student learning objective. It kind of outlines what you should be able to do when you pass this class at the end of this semester. Okay, there's no need for me to get into this too much at this point, because that's the whole idea, is to introduce these concepts over the semester. And then we have the schedule, which is tentative, and I tend not to follow my own schedule. So if I do not meet these dates specifically, don't worry. Okay, that's just the usual way of me doing things. Is that okay so far? All right. When is the final of this class? How do you find that out? Well, I do not deviate from the final exam schedule, which is right here. So if you click on this link, it will bring you to the ARC final exam schedule, which depends on the start time of a lecture. So this class starts at 4 o'clock. So that means you have to look at that list, find out the actual exam date and time. of a class that starts at 4 p.m. on Mondays and Wednesdays. So I trust that all of you can do that. We should make that a prerequisite of this class, knowing how to find the final exam of a class. Talking about prerequisite, this class does have prerequisites. It's, I think it's Math 370 pre-calc and a co-requisite of cisp430. Okay, so neither matches what I really need you guys to know before taking this class. Basically, I need you guys to be comfortable with math concepts. Now, obviously, Boolean algebra, propositional logic, those are the things that I'm going to introduce in this class. So, if you don't have any previous exposure, it's not a big deal. But I would say algebra is important, okay? And algebra is the prerequisite of pre-calc, if I understand it correctly. Is that okay? So algebra is definitely important. For cisp430 as a co-requisite, it's great if you can take it before or in the same semester. If you cannot, you can still take this class at your own risk. Okay? So here I said it. It's up on YouTube. It is recorded. You can do so at your own risk. Now, the reason why I said that is because in 430, they will talk about some algorithms that depend on recursion. In this class, we don't talk about recursion that much, but we do talk about proof by induction. And those concepts, even though one is a proof technique, the other one is a programming concept, they match up almost exactly. Okay, they go hand in hand. So if you do not have any experience writing code that is recursive or have a good understanding of what recursion is, that can be a problem. Okay, now I'm not saying that people who have not programmed recursive algorithms before are going to fail in this class. That is not what I'm saying. But what I am saying is exposure to recursive algorithms in cisp430 can be very beneficial in this class. Yep. There will be some coding. There will be some coding, but the math concept, like proof by induction, is closely related to recursion. So that's why that is a very important concept to get. And 430 does introduce recursions. All right. Let me see. Do we have any? You can pull a chair if you don't mind, and as long as the fire department doesn't show up and shut down the class, I'm cool. All right, so the actual syllabus, okay? So the actual syllabus is on the second link, and this is what it looks like. It can be available in PDF or also in HTML. For those of you who like to print out everything and put it in a binder, go to the PDF, print it out, and then you can put it on in a binder. And for those of you who just want to read it online and just check out things, you can read the HTML version. Most of this is really just common sense, so I'm not going to spend a whole lot of time to talk about it. But it doesn't mean that you don't have to. You can just ignore that. So what I'll do instead, this is the first semester that I do this, is I made a little video presentation of the syllabus itself. But because this part is common to all my classes, I make one single video for all my classes. So go ahead and watch this one. This is on YouTube, okay? But there's a link directly to that presentation. So I encourage you to open up the syllabus on one side and then watch the video on the other side. So if you have any questions about what I write in the syllabus, you want to bring those questions either back in class if you think other students may have the same question, or come to my office hour if you think, okay, maybe it's just me having that question. So you can come to my office hour or contact me by email and so on. How do you contact me? Where's my phone number? Where's my email address? It's in the syllabus. Where do you find the syllabus? It's in Canvas. Is that okay? So can I assume you guys know how to find out ways to contact me other than meeting in class? Okay, cool. So we are basically done with syllabus. And we are only about, 12 minutes into the class. So we'll see whether this works or not. Okay, if at the end of the semester, I end up with a whole bunch of people saying, "But you didn't tell me about blah 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 blah," then obviously I have to go over the whole thing at the beginning. So I am going to pass the roll sheet around. It has everybody who is enrolled in class, everybody who's on wait list when I printed this roll sheet. If you're not on here, that's okay. Just add your name, but do not take any permission numbers just yet. Okay, I will send you the permission number at the end of the class. Is that okay? Is there anyone here who is not on wait list, who is trying to add to the class? Okay, so people who are trying to add to the class are all on wait list? Okay, so I can just go through the wait list and then send you guys the permission number that way. Okay, so I'm going to pass this roll sheet around, and then we can get started. Oh, by the way, there are two more items I need to kind of mention from the syllabus. One, the first day of class is important. If you don't show up on the first day of class, I can drop you. So that only applies to people who are now watching the YouTube video from home. Okay, so I'm going to drop those people. So you guys have nothing to worry about. The second one is you can miss up to 2 classes without excuses, but the third one is going to count as excessive. Okay, and excessive absence means I can drop those people as well. Is that okay? All right, so now we can go ahead and start with the content here. This link is really optional, okay, for those of you who want to find out about your personality types and so on and so forth. I put fun stuff in parentheses because there are people who dispute whether MBTI is actually valid or not. Okay, so don't take it seriously. But if you want to find out your own personality type and see if the description matches yours, it's a cool thing to do. Okay, it does match mine. Okay, my personality type does match the test results. But there are people who claim that it doesn't match at all or it is useless. So take it with a grain of salt, okay? This is not a psychology class. So why do you think I put this up on my Canvas site? No idea? Yep.
To identify what type of learning you want?
Exactly. Okay, so you can use this to identify how you learn. And you can also use this to identify how I teach, okay? So if there's a mismatch, then we have to do something, right? So it's better to have an understanding, than not to have that understanding. So just for your reference, I'm an INTP. I can see some people writing it down right away. So INTP, the quickest way to remember that is an integer, a variable called P. Right? INT space P. If you don't get that one, I'm going to send you back to CISP 360. All right. There's also INTJ, so so P and J are the 2 variables you can have as integers. All right. So, this syllabus stuff is old. I'm going to hide it. Yeah, I'm just going to hide this one so you cannot see it. Oh, it's already hidden, so you can't see that. Never mind. All right, so getting to the introduction part. By the way, there's no textbook to buy. All the material that I want you guys to read is already on this website. I might add additional material in the semester, okay? But what you already see here are the things that you can count on, okay? And I will tend to introduce the material in the same order. So if you want to know, okay, I got a little bit of time, I want to read ahead of time, what should I read? Just read the next one, okay? So I usually follow this particular order. All right. So this link, talks about, taking a class from TAC. So you can read it if you want to, but if you don't read it, it's not going to be on any of the exams. And it looks like, it points to the wrong. Okay, it points to the wrong server. That server is no longer there, so I have to adjust that. Okay, there we go. Okay, you can send me an email to remind me to do it. So it does talk about personality types. Talks about what types are overrepresented in computer science and related career. It doesn't mean that if you're not fitting one of these patterns, you will not be able to work in computer science, or if you're not one of the quote unquote overrepresented types, you will not succeed. That is not what I'm suggesting at all. Okay. Look at this as an aptitude test. Okay, these personality tests, can be kind of looked at as an aptitude test. So it does talk about me as an INTP type. Okay. And the last part has to do with potential issues or potential patterns of how I communicate with other types. So, once again, take it with a grain of salt. Some people look at MBTI as a source of entertainment and only that. Okay, some people look at MBTI as horoscope. So, would you use horoscope to tell you what class you should be taking in the next semester? Probably not, right? So that's basically, take it with a grain of salt. Okay, do whatever you want with it. But I personally find it somewhat useful, so that's why I include it here. All right, so we'll start with Boolean operators as a review of things that you should be familiar with already. Is that okay? All right, so let's go ahead and get started here with Boolean operators. So all the content, okay, I have to fix this too. Okay, so if you get to a link that doesn't work because it is referring to moodle.lostreals.edu, you can just adjust the website. I will do it as much as I can remember. So if you just change the server name to arccis.net, that should fix 99% of the problems of that website doesn't exist anymore. Okay. All right. So we'll take a look at Boolean operators that we should be familiar with already, how we look at those operators in this class, and then we might introduce one or two operators that are not available in C and C++. Okay? How many people have taken CISP 310 from me in the last year or so? Okay, there are a few. So you guys already know that there's the only one of the operators that can define every other operators is the NAND gate, a negated AND operator. But we are not going to start with that in this class. But I just want to kind of connect what we talk about here with CISP 310 for those people. So we'll talk about the common operators that you already know. The first one is a conjunction, which is a fancy name of, how do you call this in C++ and almost every single other programming language? We call it AND, A-N-D, AND. Conjunction is AND, okay? In C++, what is the symbol representing AND? Double ampersand, very good. Not single, okay? Has to be ampersand, ampersand. Single ampersand is a bitwise AND operator. Double ampersand is a logical operator. They are not the same thing. All right, so we only care about the logical operator at this point, so we are only considering ampersand, ampersand. In mathematics, it is represented by this symbol. Kind of looks like an inverted V. Okay, so in this class, I would use a variety of representations. Okay, sometimes I would use C and C++ notation. Sometimes I would use this notation, the mathematical notation, and other times I'll use engineering notation, just so that you're familiar with, most ways of representing the same thing. So this is a table. Basically, each cell, okay, is representing the result of X and Y. But X has what value? Y has what value? Well, it depends on, so this entire column is when X equals to 0. This entire column is when x equals to 1. This entire row is when y equals to 0. This entire row is when y equals to 1. So the intersection of the row and the column will tell you the result of x and y based on the values of x and y. Is that okay? A very cumbersome way to represent the truth table, but nonetheless, a way to represent the truth table. So is this consistent with what you understand of the logical AND operator? The only time you have the result of a 1 or true is when you have true and true. So in this class, I also use 0 interchangeably with false, and I use 1 interchangeably with true. So are there any questions? No questions? All right. So just a quick check. In C and C++, what is true? Ah, you got it. Okay, I was hoping somebody's going to say 1. Then I go like, then what about 2? That is absolutely correct. In C and C++, anything other than 0 is true. 0 is false. Okay, very good. So if I scroll down a little bit, then we move on to a slightly different way of looking at a truth table. So in this case, y is this row here. X is, okay, y is here, x is here, and then each cell, it's the same thing as the other one, except I don't repeat the expression x and y. Is that okay so far? So once again, the value of y are controlled by the rows. The value of x is controlled by which column. And then the intersection between the row and the column is going to tell you what is the value of x and y for those specific values. Okay. And then moving down here a little bit, we talk about the multiple ways of representing conjunction. The first one you should be very familiar with already. Ampersand is how you represent conjunction in C and C++, along with many other languages that are also C-based. Okay, so no big deal there. The second one is the mathematical symbol. Okay, looks like a little inverted V. But in engineering, a lot of times people look at conjunction as quote-unquote multiplication. So it is not uncommon that you will find x times y, or simply written as xy, as x and y. In the context, x is Boolean and y is Boolean as well. Is that okay? All right. So I personally like to use this kind of notation because I don't have to type nearly as much. Okay, to enter the form like this, I have to type x \wedge y. Okay, as in WDGE, that's the LaTeX code to enter this mathematical symbol, as opposed to XY. So now you can start to see why I like the simplified version. Are there any questions about the notation of conjunction? Starting with the programming operator, all the way down to the simplified version that engineers like to use. No questions? All right. Moving on to disjunction. So disjunction is basically OR. Okay, so using the same kind of truth table, this is controlling the value of y, this is controlling the value of x, and then each individual cell here is the result of x or y. Okay. The mathematical symbol of OR looks like a V, but it's not exactly a V. Okay? So is that consistent with your understanding of logical OR? The only time the result of a logical OR is false is when you have false or false. If at least one side of an OR is not false, then the whole thing is going to be true. Is that making any sense? Okay, cool. So the next part is really just looking at the symbols. So what we know is x or y in C++ is double bar. And then we have the mathematical symbol that looks like a V. And then in engineering, we usually use a plus to represent or. Now, we are definitely overloading, okay? We're using object-oriented programming concepts. We're definitely overloading here to say the multiplication symbol also means conjunction when the type of the operands are Boolean. Is that making any sense? In the same way, we are overloading the plus symbol to say that if x is Boolean, y is Boolean, then x plus y is representing x or y. Is that okay? All right. So this means I don't want people to tell me true or true is 2. Okay. And then we have negation. Negation is represented by a little cliff symbol in mathematically speaking. This is negation here. And this is a really simple table. If each column is representing a value of x, when x is false, not x is true. When x is true, not x is false. Okay, that's a pretty simple one. So are there any questions so far about the operators that we are familiar with already from C and C++? Okay, no questions. So negation has a few representations. In C and C++, it is represented by the exclamation point symbol. That's the logical not operator. Quick quiz. What is the bitwise not operator in C and C++? Negation. No, there's a single operator to mean arithmetic negation. Not arithmetic, sorry, Boolean negation. Logical negation. Bitwise not. No one knows? It's the tilde symbol. Okay, that's what the tilde symbol is for. Mathematically speaking, it's the little cliff symbol, a bar and then a drop. But in engineering, if you go into electrical engineering or computer engineering, you might encounter an over bar to mean logical negation. And if you look at circuitry or the documentation of chips, they might use a single slash before whatever symbol it is that it wants to negate. So these are alternative representations that you might encounter, not in this class, but in other classes. So which one do you think I prefer? Because I'm lazy, I don't want to type a whole lot. This one is fairly easy, okay? But it does have a confusion thing because it looks like division, right? So I'm just going to use exclamation point in this class to mean negation, because that it doesn't. Well, I guess later on it can be confusing because it's also factorial, but factorial goes after the value. If it is before the value, it is logical negation. Is that okay? All right. So now we are done with all the operators that we should be familiar with already. But in this class, we also introduced some other symbols. One of them, okay, and this one is really just for people who have taken CISP 310 or will take CISP 310 from me. It's called negated AND, which is also why it's called NAND. The first N stands for negated, and then the AND is what it is negating. So the definition of X NAND Y, okay, the up arrow is for whatever reason, the standard of, negated AND. I'm guessing it has to do with the AND looks like this part of the arrow, and then the bar means negated. Okay, that's just my guess. But it really means the same thing as the negation of the conjunction between two values. That's NAND. Okay? Now, the reason why NAND is interesting is because if we just define NAND as the one and only logical operator, I can use that to define every other Boolean operator that I need to use. You guys don't like, it doesn't seem like you believe me. I know Nick is believing. Okay, so negation of X is X NAND X. Does that make sense? A value NANDing with itself, which means it's a value ANDing with itself and then negating the result of that. That's the same thing as negation. X and y without the negation is x NAND y NAND x NAND y. Well, that's because x NAND y gives me the opposite of what I want, right? So I want to negate that. But how do I negate something? NANDing it with itself. So that's why x NAND y the whole thing, NAND x NAND y the whole thing, gives me just regular x and y. OR is a little bit more tricky because the OR has to do with De Morgan's law. I have to turn OR into and then do the negation stuff. But in the end, it is x or y is x NAND x NAND y NAND y. It has to do with De Morgan's law, which we'll talk about later in this class. Is that okay? So once again, NAND is not something that is super important, but I would like to point it out because it is a really cool Boolean operator that can be used to define every other Boolean operator that we need to use in this class. Which also means in a programming language like C and C++, they could have just given you NAND, and that's all you need. It does make your program a little bit harder to read. But it can be done. Well, just because it can be done doesn't mean it is necessarily a good idea, does it? All right, so here starts the actually important operators for this class. Implication. So implication can be defined as the negate x implies y, can be defined as not x or y. So that's one way to look at the definition of implication, is really just expanding x implies y to something that we already know. The negation of the negation of x or y. Okay? The other way to look at this is to look at it as a truth table. Okay? When y is false and x is false, x implies y is true. That's how you read the table. When x is true, y is false. True implies false is false. That's how we are reading this table. Is that okay? Okay, let me be more specific. Does everybody understand how to read this table? Not necessarily what implication is, but just how to read the table. Okay? So, does it make sense to you? Yes? Sort of? No? No, doesn't make sense. Okay, very good. Now I can explain it a little bit more. So let me see what I have here, because this is very good. Okay, so I do have this. So let's say at the beginning of this class, I ask everyone in class to contribute $1 so that I can give you words of wisdom. Okay? And my words of wisdom is, a blue cat is sick implies tomorrow is doomsday. You pay $1 for that. Okay? So this is a statement. It's either true or false. Okay? So if you don't want to look at this statement from the perspective of true or false, the easier way to look at it is, can I get a refund at the end of the semester? Because the statement turns out to be false, right? Okay, so now the question is, when do you think you can get your refund? Because you can prove me wrong. Is that okay? There are 4 scenarios. So this is the rest of this slide spells out the 4 scenarios. Okay. The first scenario is a blue cat is sick today or yesterday, and today is doomsday. Is my statement true? Can you get your refund? The blue cat is sick, and then tomorrow is in fact doomsday. So this is true, and this is also true. Can you get your refund back? No. You cannot get your refund back because what I said was true. Okay, that's easy, right? That's the easy one. So moving down to the next one. Okay, so we'll look at it from yesterday's perspective. Okay, so yesterday you did not you do not observe a blue cat being sick. Now, it can be because there are no blue cats to begin with. It is also can also be because all the blue cats that you can see are not sick. Okay, but nonetheless, okay, this particular statement was not true yesterday. Is that okay? But guess what? Today is not doomsday either. Everything was fine. Can you get your refund? Nope, you cannot. Why not? Exactly. The statement did not say anything about what should happen when you cannot find a blue cat that is sick. Okay, so you cannot get your refund this way. That would also explain the next one, right? Because the next one also starts with the same premise. Yesterday, you could not find a blue cat that is sick, okay? But guess what? Today is doomsday. Now, of course, if today's doomsday, the last thing you need to worry about is to get your $1 back. But to be, logically correct and valid, we want to, see whether you should get the dollar back today or not. Should you get your dollar back when yesterday you could not find a blue cat that is sick, but today is doomsday? Can you get your money back? Because I told you something that is not true. You cannot, because what I said is only going in one direction, okay? Meaning that if you can find at least one blue cat that is sick, then today has to be doomsday. I didn't say a single thing about what if you cannot find a blue cat that is sick. So the outcome of that one can be either way, okay? Because they will both be consistent with my original statement. So moving down here, the only time you can get your money back is yesterday you found at least one blue cat that is sick. And then today is not doomsday. That is the only time you can get your money back. Is that right? So are we doing okay so far with the concept of implication? Okay, so this is kind of the long way of looking at implication, because the shorter way of looking at implication is really just look at the truth table, or look at it by its definition. This is the definition of implication in logic. X implies Y is equivalent to the negation of X or Y. Yep.
Can you phrase it the way you did when you said false implies false is true, and then so it's
Yeah.
false implies true is false, and then true implies false is true?
True implies false is false.
You it's true, I think.
True implies false is false.
What about the one under it?
This one?
Left one?
This one?
Down.
This one?
Yeah.
This one is false implies true is true. Because if the premise is false, the outcome can be true or false, and the conclusion will still be true. The implication itself is still true. So it is tricky because it's doing some little mind trick, because we understand implication in a certain way, but in this particular case, this is the actual mechanical definition of implication. Is that okay? All right. So I'm moving things a little bit out of order already. This is only the first class, and we're only about 40 minutes into the first class, and I'm already moving things out of order, because I want to talk about what a mathematical proof is. How many people have done some mathematical proofs at least once, okay, in your other classes? I don't care what it is. It can be algebra, can be calculus, can be linear algebra, okay? So plenty of people have done proofs already. What is a proof? What is one step of a proof? What does it mean when you say this follows this? You have to prove the second statement is true, but only if the first one is true too. Okay? So when you prove a theorem, what you're trying to do is to start with a whole bunch of stuff that is known to be true. Either they are known to be true, they're called axioms, or just given by the teacher. Assume x equals 5, right? So you start with things that you are told to be true to begin with, and then each step is getting it to the next representation, which is also true, but it needs everything else, the beginning stuff to be true to begin with. So you're basically following this link, these links, until you get to the representation that you're looking for, the theorem that you're trying to prove. So that's why implication is important, because it tells you what steps you can take in a particular proof. And proof is a big thing in this class. We'll do quite a bit of proofing in this class. So that's why we need to understand what implication is in order to get that done. So are we good so far? The usual operators, not and or, okay? And then plus this extra implication operator. There's one more, but that one is easy to define. So the last operator in this particular module is equivalence. So equivalence in return is defined by conjunction and implication. X is equivalent to y, or x if and only if y, there are multiple ways to look at this, is basically the same thing as x implies y and y implies x. And that's just the definition of equivalency. One thing I haven't really used in the slide is to look at things from the perspective of necessary versus sufficient. Okay? X implies y means x is, okay, sufficient. Yep. X implies y means x is sufficient to lead to y. Nothing else is needed. If x is true, y has to be true. Is that okay? So from that perspective, equivalency is, if and only if, is basically saying x is both sufficient and necessary for y. Is that okay? Because depending on how you understand the words, sometimes sufficient versus necessary is a better way to explain implication. Yep. Necessary means it is one of the conditions that is needed. So when you have x implies y, there are two ways to say x implies y. One is to say x is a necessary condition of y, but you can also look at it in the opposite direction and say that y is a necessary condition of x. Okay? All right. So are there any questions about these things that we have introduced in this particular slide? This is all good? All right. So let's go ahead and move on then. Now, if you remember there's a question, or if you just think of a particular question, it's always okay to go back to a previous topic and ask that question. So what we'll do next is we'll talk about set theory. And I understand that some people have some exposure to set theory in high school, and some people may not have any exposure to set theory in high school. Is that right? How many people have some exposure to set theory from high school? Okay, so so there are some people who may not have any exposure. That's fine. It's not a problem. All right. So we'll talk about what is a set and its elements. So you can look at a set as a containment, okay, as a collector, a bag of elements. So that's pretty vague, right? What is a bag and what is an element? So the most basic concept is containment, whether something is in a set or not in a set. So elements are the individual things that can belong to a particular set, and a set is potentially a collection of elements. So that's awfully vague, isn't it? Okay, that's okay. We'll clarify when we introduce the symbols and other things. So I'm going to give you an example right here. T is a set. And as a set, it contains the elements as follows. It contains the element 12, 5, 2.2, 7, -1, and 10. So in this representation, the curly braces are necessary, and they have to be curly braces, because that's the representation of what is inside a set. So if you forget this part here, open curly brace, blah, 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 close curly brace, in mathematics means we're dealing with a set. What is between the curly braces are the elements of the set. Is that okay? So I'm only defining that T, uppercase T, is the following set. That's all T equals 2 is doing. Any questions about this? So the next point is, how do we list items inside a set? You can see that this is not in order, right? It's not sorted. That's okay, because ordering within a set does not matter. So I can represent exactly the same set if I sort it and start with -1, 2.2, 5, 7, 10, and then 12. That represents exactly the same set as T. Is that okay? You cannot have two elements of the set having exactly the same value. In other words, I cannot list -1 twice or any value twice in a set. That is not allowed in a set. So now you got two things that you also have to remember. Ordering is insignificant in a set. And two, all elements in the set they have to be distinct. You cannot have duplicate items in a set. Is that okay? All right. So now we introduce the symbol of what is an element of. So in this case, you can see in this expression is asking the question, is 2.2 an element of T? That's what it's asking. Well, in this case, it is. So 2.2 in T is true, because 2.2 is in fact an element of T. Is that okay? And on the other hand, if you look at this expression here, 23, now this particular symbol that looks like a little e, or it looks like a really kind of funky way to write uppercase E, there are two ways to spell it out. You can spell it out simply as in, I-N, or an element of, okay? It's your choice. So you can say 23 in T, or you can say 23 is an element of T. Both way works. But it is a Boolean expression itself. It can either be true or false, okay? So if T is defined this way, is that expression true? 23 in T, is that true or false? It is false. Very good. Okay. So I just want to emphasize, when I use this particular symbol, the expression itself can be true or false. It by itself is a statement that can either be true or false. Do we have any questions about the basic set notation stuff? Curly braces enclose elements in the set, and then the lowercase e thingy, is element of. Is that part okay? Yep, go ahead. Sorry?
What about subsets?
Subsets. Okay, we'll talk about that later. Okay, but I cannot talk about subset until I'm done with elements of, because that's one way to define subset of. Okay. Well, if that is the case, so far so good. And I'm going to use my notepad here. This is from my earlier class. I'm going to delete all of this stuff here. What do you think this is representing? First of all, is it a set? It is a set because it starts with open curly brace, ends with close curly brace. Okay, so it is a set. But is there anything in this particular set? There's nothing in the set. So it is a set, but it's empty. How shall we call this? It's called an empty set. Exactly. It's called an empty set. Do you think an empty set is useful? the concept of it is useful, okay? And we'll see later on, a lot of things that we'll talk about in this class depends on set theory, and that's why we have to talk about set theory first, because then we'll have the vocabulary to discuss all of the more advanced topics. So that's an empty set, and in this class, this is the only way that I write an empty set. There are alternatives in math classes too. Okay, so moving on down the notes here. So the first question is, how do you represent a set as some kind of data structure in C and C++? What do you think? Sorry? An array. So arrays are kind of like a set, but it is not exactly a set in two ways. Because in an array, things are kind of ordered. Okay, so if you think about an array of two elements, okay, first element has a value of 16, the second element has a value of 23, okay? So when you compare an array 1623 with an array 2316, unless you don't do some tricks with the comparison, they are not considered the same array. But when you look at those as sets, they are supposed to be the same. So it's difficult to represent elements in an array, but make the ordering not important.
Wouldn't you just be able to like go through one array and be like, if you don't find any of these numbers?
You could do that, yep. But the typical way of doing comparison, using the same index doesn't work anymore when you use arrays to implement a set. Yep. So this is an open-ended question. I don't need you to answer the question right now. Some people who are more advanced in C++ programming would point out, oh, there's a template called set in C++ in the standard template library, and they do implement the concept of a set using the set template. Okay, so there is that. So the next question now, going to section 3, is how do we know whether two sets are the same or not? How do you compare sets for equality? Yes? Sorry, say that one more time. Right, so, but how do we express that? Yep. Implication. Okay, so can you be more specific?
So for the first case, if x is in S, that implies that x must also be in T if these two sets are equal. Also, converse, x is in T, that implies that x must also be in S.
Mm-hmm.
Those two sets together.
Yep. So using equivalency, because you're relying on the implication to go both ways. Because what you're saying is, if you can find if everything in the entire universe, okay, follows this rule, okay, if I just pick anything from the universe, okay, we'll call the thing that I just picked out as x, okay, and the two sets that I need to compare, we'll call one S and call one T, okay. So you basically pick out anything in the entire universe, okay. Then you have to say, if this thing is in S, it also has to be in T. If it is not in S, it cannot be in T, and vice versa. Okay. So it's kind of vague at this point because we have not introduced quantifiers. So that's why we are kind of lacking the vocabulary that we need in order to express equivalency. That means, well, if two sets can be compared, okay, and say this is the same as that, okay, can we have a set where at least one element of the set is also a set? Well, I don't see why not. Okay, so let's go through some exercises, regarding that. Okay. All right, so we'll start with simple stuff. Okay, A, B, C is the same thing as B, C, A. Is that true or not? Is this, is this equality true or not? It is true, but they're in the wrong order. There's no such thing as wrong order because ordering is not important when you're talking about elements in a set. Okay? Yep. Yep, we will get to that. We'll get to permutations and combinations. So set theory, or the concept of a set, definitely it relates to combination, but not so much permutation. Okay, so everybody's buying this. Okay, so we'll say, no, it is true. Okay, not using set comparison, can I say 12 equals to 12? It's not a trick question. It is true. Okay, very good. I'll just throw in one more thing. Is that true? An empty set is the same thing as an empty set? Okay. That sounds really Buddhist, by the way. Nothing is the same thing as nothing. All right, so they're all true. Very good. So now that we know that the set containing ABC is the same thing as the set containing BCA, we know that 12 is the same as 12. We know that the empty set is the same thing as the empty set. Let's check this out. Okay? So now I start another set here, which has the empty set as an element, 12 as another element, ABC as yet another element. And I'm asking, is it the same thing as another set? And in the notation, I start with BAC, and then the empty set, and then 12. So is this condition true or false? It is true. Very good. Yep.
So if you're saying it's true, it means if it would have been instead of 12, it would have been 21. It would have to be true too, because
Say that one more time.
like I mean that if you're saying that this is true, then then it would be 21. If it would have been 21 instead of 12, it would have to be true too, because each element of the set is the specific fixed element, as far as I understand. No, or it has to. Never mind. Okay, whatever.
Well, if you substitute 12 with 21 on both sides of the equality,
Just on one side.
or just one side, then it would not be true, because then you have an element that is only in one side but not the other side. Yep. Say that one more time. Well, that's what we are having here. Yep. No. Well, okay, the only restriction is a set cannot contain itself as an element. So that's the only rule that you have to observe. It's good? Okay. So in many cases, you can look at a set as a folder. Okay? Can a folder contain individual files? I mean, I'm talking about actual computer folders now. Yeah, okay, that sounds pretty ordinary. Can a folder be empty? Can you make a folder that's nothing in a folder? It's an empty folder, right? Can a folder contain another folder? Yes. Same thing, okay? The only difference between the concept of a folder versus the concept of a set is when you look at the content of a folder, you can quote unquote sort it in different ways, okay? But in other ways, you can say they are the same, because how you sort and list the content in a folder, you can do it by name, you can do it by the last modification date of the file, you can do it by extension, and so on and so forth, which basically means there's no actual inherent ordering of the content inside a folder. It really is just how you want to visualize and list the content, but there's no actual ordering of content in the folder. So that might be one thing that you can kind of keep in mind, is a set is really just like a folder. It's a container of some kind. And it even works from the sense of you cannot have two files of the same name in a folder, can you? You cannot. So that's kind of helpful, because that kind of gives you something that's concrete that you understand already, and it's very, very close to a concept, an abstract concept that we are talking about here. Is that okay so far? Cool? All right. So then we just talk about a set as an element of another set, basically, yep, and we can drill it down to as many levels as you need, okay? Cool. And this part has to do with a reference that does not exist. I have to fix that. So section 5 starts to talk about, how do we denote a set that has an infinite number of elements? Okay. So let's consider a set of all integers. Okay, how many elements are in that particular set? How many integers are there? Well, I didn't quite ask that question very specifically, did I? Because if I said the integer type in C and C++ programming, it is finite. Okay, it depends on whether we are talking about 32-bit integers, in which case there are about 4 billion of those. And if you're dealing with 16-bit, we have 65,000-ish, of those integer values because it's finite. But when we are talking about integers from a mathematical perspective, there's an infinite number of integers. Okay. Then how do we represent, let's say, a set of all even numbers? Well, this is kind of one way to do it. Okay, you just kind of list out a few elements of that particular set and hope the reader understands how this pattern is going to continue. Right? So it goes like 0, 2, 4. The next one is going to be just plus 2, plus 2, plus 2. And then on the other side, you get -2, -4. And then the next one is going to be -6, -8, and so on. But that's a lot of implication. That's a lot of vagueness in this. There's a lot of ambiguity. Okay? So we don't like to do things like this. Okay? So that it relies on the interpretation of the reader of what it means. So what we'll do is we're going to introduce this particular construct here. So E is still a set of all the even numbers, but this time I'm going to use a kind of different way to express it. So we'll focus on just the part that I'm highlighting here. We have open curly brace and close curly brace. Okay, so that means whatever is in between is describing the elements of this particular set. Is that okay? So we take the curly braces out of consideration. We focus on what is inside. So we have X here. Okay, so this X is basically giving a name to something that is in this set. Okay, because in order to tell us, what properties, it has to meet, I have to give it a name first, right? So X is really just a name saying, okay, if X is an element of E, it has to have the following properties. Okay, or if anything that has the following property, it has to be an element in E. So it goes in both directions. Is that okay? So X is really just a name that I give to something so I can describe it. So how do I describe X? Well, this is a Boolean expression. And let's see how much you remember from your CISP 360 class. The first part, how do we read this? It's a symbol that we just introduced about 15 minutes ago. X is in Z. Now this kind of funky looking Z means the set of all integers. Okay, so what this part means is X is an integer. Is that okay? What about this part here? X mod 2 equals to 0. What is that? What is mod? X mod 2 is the remainder of X divided by 2. Okay, so if X as an integer has a remainder of 0 when you divide it by 2, well, that sounds like an even number to me. So if these two requirements are both met, then it is an element of E. So something is in E if and only if it is an integer, it is an element of the set of integers, and when you mod 2 with this thing, it gives you 0. Yep. Z is defined somewhere here. Or did I? Oh, okay. Did I define it above? Yep, there we go. Is that part okay? I didn't read my notes sequentially. Yep.
So -2 is in that set. If we replace mod with division, we'd have -2 divided by 2, which is -1 equals 0. Is division and mod not equal?
Ask it one more time.
Are division and mod not equal on negative numbers?
That depends on how you want to do division. But we know that if x is -2 or -4, the remainder is going to be a 0. So as long as the remainder is 0, it will still meet this requirement. Now, if you ask -3 mod 2, does it have a remainder of 1 or does it have a remainder of -1? They can both be right. Okay, it depends on how you look at the process of division, because the only requirement it has to meet is the quotient times the divisor plus the remainder has to equal to the dividend. And the remainder has to be within a certain range of relative to the divisor. Question back there? No? Okay, I thought I saw a hand earlier. Okay. So are we still doing okay so far with the notation? How to describe what is in a particular set. With a finite set, you can just list everything in it. Okay. With a set that has an infinite number of elements, this is the notation to do it. Is that okay? All right. So if there are no questions, then we'll generalize and say, okay, so here we are looking at p of x as a Boolean function. So if you want to relate this class to programming, actual programming, look at uppercase p as a function in C and C++ that returns a Boolean type. Okay? It can be very simple, can be very complex. I don't care how complex or simple it is. It just returns a Boolean value. Okay? So this notation here, okay, E equals to a set. It basically means if and only if P of x is true, x is an element of E, which is what we are expressing here. So it's just an explanation of the notation itself. This notation means exactly the same as this. That's all. Is that okay or not? Because this is abstraction. I'm abstracting from the example of even numbers and make it even more abstract and just say that give me something, a function that returns a Boolean type. Okay? And I can then use it to define membership of a set. Yep.
Don't they sometimes move the x as an element of integers to the left of the bar and then just use p of x as the x mod 2?
Well, okay, in the case of a mod, if x mod 2 is 0, it kind of implies that x has to be an integer as well. So 1 is already implying the other one.
But I mean, I'm guessing sometimes you'll just see that x is an element of the integer or something on the left side of that bar you have, and then
The left side of this, oh, you mean this bar here? So x is on,
from above,
so
yeah,
x is an element of z is on this side.
and then bar is the statement.
I suppose you can do that, but I just kind of stick with this notation, and p of x, remember, it can be anything. What if p of x is true, just the constant truth? Just kind of imagine in your head you have a c function that returns a non-zero value all the time. What does that mean? What is going to be this particular set in that case? It's a set of everything, right? Because you can give it anything and it will say, yep, it should be in that set. What kind of stuff are we talking about? Can be anything. You can have anything in a set. Okay, you can have values like numerical values. Sure, you can have that. You can have strings. You can have people, cars, molecules in the air, and so on and so forth. So everything can be potentially elements to be considered for membership in a set. Now, given that, in this class, we are mostly just concerned about numbers. All right? So are we still good so far? Okay. So this is really just spelling out what the notation is. This is basically saying exactly the same thing as this. And you can see how we are already using operators that we have talked about a little bit earlier in today's class. All right. Any questions before we move on? Any questions about the notation? Now the bar, if you want to spell out this bar here, some people call it such that. Okay, x such that p of x is true. We talked about the empty set already. Okay. Let me give you a very short quiz here. And I'll give you the name so I can refer to it. Okay, so X is defined to be the following. So the question is X an empty set? It is not an empty set. X itself is not an empty set because it contains a single element. That element turns out to be the empty set itself. But X itself is not empty. Think about folders, okay? If you look at this, it looks really confusing. Why X is not empty? Think about folders. X is a folder that contains another folder, but the nested folder itself is empty. So the parent folder is not empty. It does contain one item, but the item that it does contain is an empty folder. Is that okay? All right. Yep.
I understand that you got an empty set inside a set, but technically isn't that, well, no, never mind, because you got never mind. I was thinking that it's actually contained in itself, but it's still actually an element, so never mind.
Yep. If you want it to be more physical, you can consider a set as a box.
Yeah.
So you have a box that contains a smaller box, but the smaller box has nothing in it.
Right.
So when I ask you, is there something in the outer box? The answer is yes. Yep.
Show one example of a set containing itself as an element, then?
You cannot. That by definition, you cannot have a set containing itself. So even for notation purposes, you cannot say something like this. This is invalid in set theory. So you cannot say X, give it a symbol, is a set of itself. That is not valid. That is invalid. So it is always false in this case. Oops. All right, so we'll now take a look at what can we do with, set operations. So the first thing we encounter is the intersection. So this kind of inverted U symbol means intersection. So we are talking about the intersection of A and B. What does that mean? Well, the intersection of A and B, A being a set, B being a set, is by itself a set. Okay, so the first thing we notice is the intersection of two sets is by itself a set. What's in it? Okay, so E such that, okay, so everything that is in the intersection, okay, I'll put it the other way, I'll use the other notation. If you can find something that is in A and also in B, that something belongs to the intersection. Okay. On the other hand, if you take anything out of the intersection, if you take an element out of the intersection, you know that that something is in A and in B. So it goes in both directions. Is that okay? Are there any questions about the concept of intersection? Something has to be in two sets, not necessarily different. Well, if there are no questions about this, I'll give you a trick question then. Okay. The first trick question is I can't really write the inverted U using a text editor, so I'm going to say intersection Y, which basically replaces the little inverted U symbol. Oh, let's make it X here. What do you get? You get X back, okay? Because if you look at every single element of X, is that element in X? Yep, so there you go. All right. All right, so we got X here. What about this? X, I don't know what X is, but I know I'm intersecting it with the empty set. What should I get? The empty set itself. Right? Because any element in the intersection has to be found in both of those sets. What is inside an empty set? Nothing. So the intersection with the empty set has to be empty. All right. So far, so good. So this is just the other way to spell out, what intersection means, but this time using membership, element of, and also the other logical operators that we have talked about, conjunction, equivalent to, and then we have these symbols defined earlier. This part here is what we want to know. Okay, we have this set A intersecting with B, so E is an element of A intersecting with B if and only if E is in A and E is in B. So you can look at this as the kind of like the mechanical definition of intersection. Is that okay? We have about a minute or so left, but I think we can cover union. The reason why I think we can easily cover union is if you just look at the definition of intersection, which is here, versus the definition of intersection, don't they look very close? The only difference is our conjunction is now a disjunction. So when you're talking about a union, it means an element is in a union between two sets if that element is in at least one of those two. It can be in both, but it has to be in at least one of those. Okay. Well, according to my watch, we got 2 more minutes, so we'll work out a few examples here. Okay. So I want to say X union with X is what? What is in the union of X with itself? Has to be X itself. Okay, so that's pretty easy. What about X union with the empty set? You get X back. That's right. All right. So are we doing okay so far with today's, with the first class? Does anyone have a chance to sign the sign-in sheet? Yes? Okay, very good. All right. So there's something you can do when you get home. So what I need you to do is we are basically here right now. Okay, we are almost done with basic set theory. Just kind of read ahead of me. Okay, finish that whole module when you have time, and if you have extra time left, go ahead and read basic quantifiers. So we'll have a little homework assignment when we cover both of those topics. So right now I don't really have any exercise for you. If you guys request, I can give you something that is ungraded. So I'll give you some problems to solve, and then I'll disclose the answer in the following class. I can do that, like between now and Wednesday. Okay. I'm good. All right. So that concludes the class. I'm going to stop the recorder.